All right, so how many times are we going to run through this while loop here? Well, what this loop is doing is it's finding the midpoint of the list. So it's essentially cutting the size of the input in half, and then either looking at the left side or the right side, and then searching for the element in that like half length list. Okay, so it's going to keep cutting in half and cutting in half and cutting in half and cutting in half. Let's call the number of times through the loop let's call that L just for now, just to give that that variable a name. That's the unknown. We want to know what is L. Okay, well, this is not exactly going to be a proof, but I am gonna just sort of like show you an example that sort of explains why the answer is what it is. So let's say the list is of length 16. I'm just going to write the indices. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh man, I run out of space. Hang on. Okay, it's just visualizing, right? So here's a list of length 16. These are just the indices, so the actual numbers in the list are something else. But what the algorithm is going to do is it's going to find the midpoint of that list, which would be here, right? And then it's going to either take the upper half of the list or the bottom or the lower half of the list, because the number we're looking for is either going to be less or greater than that midpoint, which would be 8, the 8th element. So so let's say it takes the bottom half of the list, right? It takes that. Now we have the numbers 1, 2, 3, 4, 5, 6, 7, 8. Again, it finds the midpoint, which would be here, and it's going to take either the bottom half or the upper half, right? So let's say it takes the upper half this time. Now we have 5, 6, 7, 8. It finds the midpoint, it will be here. Let's say it takes the lower half, and then 5, 6. It finds the midpoint, which is here, and then it's going to take the upper half. And now I and j are going to become equal to each other eventually, right? The left and right endpoints of the list are going to, of the search interval, are going to come together. So once you've got to this point, you've like found your element, right? So the question is, how many times is this going to happen? Well, one way to approach this is to think backwards. Okay. So going from a list of length 1, which would mean you found your element, right? If you go backwards, you're going to double the length of the list. Think of that as like multiplying by 2, and then. And then going back one step, you're going to double it again, right? And going back a third step, you're going to double it again. So what you have here is, let me think about this for a second. 1, 2, 3, 4. You should be, hang on a second, that's not quite what I wanted. Why is that not quite right? Oh, there's one more step at the end here, which is like where your list comes together. Why is there one more step? There's one more step at the end. Oh yeah, that's right. Oh, that's right. You cut your list from 2 down to 1. That's why, because I forgot to put the last step here, which is you have a list of length 2, which is 5, 6, and then you cut it down to a list of length 1, which is just 6. So there's a times 2 at the bottom here that I forgot to mention as well. I'm sorry, I didn't go quite to the end. So there we go. So now we're thinking backwards. The number of steps is essentially the number of times we had to multiply the length of our list by 2 in order to get from 1 up to the total length of the list. So this is, so 1 times, so it's going to be 1, I'm at the bottom, right? Yep, 1, and then times 2, some number of times. So the number of times is the number of times we're going to go through the loop, which is L, and that's going to equal the total length of our original list. Now, in this example, it was 16, but in general, it's going to be n, right? So what we can see here is starting from going backwards, 1 times 2 to the power L needs to equal n. Well, if you solve this for L is going to be log base 2 of n. All right. So when we're cutting in half and cutting in half and cutting in half until we get a list of length 1, it's log base 2 of the input. This number, approximately, like if you take this and approximate it as an integer, that's going to be the number of times that we'll run through the while loop. So what we end up with here, the result of this algorithm here is this is going to be 2. F of n is going to be 2 plus these 6 operations per loop, so 6 times the number of times through the loop, which is log base 2 of n, and then plus 2 more at the end. Right, so overall that is 6 log base 2 of n plus 4. So we have a multiple of a log function plus a constant. So this is big O of log base 2 of n. Okay, so that's better than big O of n. Okay, let's compare those two big O estimates. So our linear search is big O of n. Our binary search is it's also big O of n, but our binary search is big O of log n, which is better. Remember, log n is faster than n. So this is like the analysis of the complexity that actually proves that binary search in the long run, so like with large inputs, binary search is going to give you your result faster than a linear search. It might not be true for small inputs. Remember that. Let me bring up my graph again. Remember that sometimes these things don't exactly they don't satisfy the inequality all the time, right? Like in the early stages over here, you can have things kind of backwards, and so sometimes like a more efficient algorithm might take longer for small inputs. But what we care about is what we generally care about when we're comparing them is what happens with large inputs. What happens as you scale it up? When you scale up the input, the binary search is going to be better than the linear search.